So let's take on another example here and find the points of inflection and discuss the concavity of the graph of this function. In this case, f of x is the function x plus 1 over the square root of x. Now, while this might seem sort of an odd kind of function to deal with, we should talk about where we're going to get concavity and where we're not. And of course, I always establish what is the domain of our function. Well, in this case, x certainly cannot equal 0, but remember we've got a square root involved in all of this. And since that's in the denominator, we're going to say that it looks as though our domain of f is going to be the set of all real values of x such that x has to be greater than but not equal to 0. So any concavity that we have to discuss is going to have to be over this particular interval. Okay, so we're not even going to really worry about 0 so much, just as long as we have values that are greater than 0. So let's take a look at our function and its derivatives. And we're going to have to do a little bit of work right here, but that's okay. So f prime of x, what is that? Well, we're going to have to use our quotient rule. In this case, I'll use the quotient rule. And we're going to take the square root of x squared in the denominator. We'll have x to the 1/2. I'll just rewrite my square root of x this way. The denominator times the derivative of the numerator minus the numerator, x plus 1, times the derivative of the denominator. In this case, that is 1/2 times x to the negative 1/2 power. All right, a little simplification is in order right here. F prime of x, we have x raised to the 1/2 power minus 1/2 times x to the negative 1/2 power times x plus 1. Well, what does that lead us to? That seems like an odd formulation right there. Let me correct that line. That looks horrible. There we go. We've got x down here. What's going to happen? Well, it looks like in the numerator right here, we can actually factor out 1/2 times x to the negative 1/2. How would that look? Well, in this case, 1/2 times x to the negative 1/2 power. We factor that out since it's x to the 1/2, x to the negative 1/2 common factor right here. We factor that out and say, well, what would you have to multiply by 1/2 x to the negative 1/2 to get positive x to the positive 1/2? And the answer to that is 2x. All right, not bad. And then, of course, we're factoring out 1/2 x to the negative 1/2 from 1/2 x to the negative 1/2. That just goes away and leaves us with the quantity x plus 1 in parentheses here. And of course, all of that is over x. So I'm going to simplify one more time right here. In the numerator, we're going to get 2x minus x plus 1. So that negative, of course, goes to both quantities in the parentheses right here, remembering that we're going to get x minus 1 then in the numerator. And in the denominator, we're going to get 2 times x to the, let's see, 1/2 times x to the 1. But that's really like saying x minus 1 divided by 2x to the 3/2. Okay, that's f prime of x. So our next job is going to find f double prime of x, which means, of course, we can use our quotient rule yet again. So what does that mean for us? We're going to take the quantity 2x to the 3/2 in the denominator squared. We're going to be multiplying by 2x to the 3/2 times the derivative of our numerator, which is 1, minus our numerator, which is x minus 1, times the derivative of 3/2 x, 2 times x to the 3/2, the derivative of which is going to be 3 times x to the 3/2 minus 1, that's 1/2 power. Interesting. Okay, so let's see how this might simplify, if we can do so at all. Common factor in the numerator looks to be x to the 1/2, since x to the 1/2 is contained in x to the 3/2. So we're going to factor out x to the 1/2 here. That's going to leave us with 2 times x to the first, right? 1 plus 1/2 would be 3/2, so we take away that, minus 3 times x minus 1 divided by, I'll rewrite this, 4 times x to the, I'm going to write this here as 6/2, because, and you'll see that if we do a subtraction right here, canceling this common factor with the one in the denominator, here's what our denominator is going to look like. In the denominator, just so that you see it, it'll be 6/2 minus 1/2, so it would be 4 times x to the 5/2. And in the numerator, we're going to have 2x minus 3x, that's minus 3, that's minus 2x minus 3x, pardon me, that's minus x, having fun already, minus x, and negative 3 times negative 1, that's plus 3 in this case. Interesting. Okay, so our job now is we're going to use this function to help us determine where we get that positive and negative. And of course, we're looking for changes in concavity where f double prime of x either changes from negative to positive or positive to negative. So we're interested in intervals like where is f double prime of x greater than 0. All right, we're not really so much interested in this denominator changing our sign, since our number line is only going to be starting at 0, but we should be worried about what's going to happen where the numerator is equal to 0, and we would say that the numerator, negative x plus 3, is equal to 0 at x equals 3. All right, so starting at 0, we're going to see what happens. Let's see, 3 is a critical point for our second derivative. And let's pick a value within this interval. So let's choose, let's say, positive 1. What happens at x equals positive 1? Well, at positive 1, the numerator, negative 1 plus 3, is positive. In the denominator, 4 times 1 to the 5/2, so that's positive. And so that gives us a positive value. At x equals 3, we get that change. We get that 0 in the numerator. So let's pick a value that's within the interval. So x equals 4, let's say. In the numerator, we're going to have negative 4 plus 3. That's a negative number. And in the denominator, we're going to have 4 times 4 to the 5/2. Well, that's a positive number. Negative divided by a positive gives us a negative overall. So we've got a positive value all the way up to 3 and a negative value after 3. That means we have concave up shape here on the interval from 0 to 3, and then concave down from 3 to positive infinity. So it looks like we've got change in concavity right here, and so we're going to get a point of inflection where x is equal to 3. But if we want a point of inflection, of course, the next thing that we have to do is calculate the value of the function at x equals 3. So we're going to go up here, and it's going to be 3 plus 1 divided by the square root of 3. We're substituting into the original function way up here, right? F of 3. So there we go. 3, 4 over radical 3. That is our point of inflection for this curve. And that's what we wanted to find out. So we're done.